coming out to listen to me in my presentation today. Can you all see my screen okay?
Yes, perfect.
Okay, awesome. All right, so my name is Isaiah Osborne. I am a student at Middle Tennessee State University. I just finished my bachelor's degree in mathematics. I'm getting ready to start my master's degree in computer science this fall. So I've been working on this as a undergraduate research project for the last 2 years. Before I get started, I would like to say thank you so much to my wonderful faculty mentor, Dr. Dong Yi, for all of his help and support with this project, and also to MTSU for their generous support of my project with 2 undergraduate research grants. Okay, so just to go through some quick terminology and everything before we get into the actual presentation itself. So all the graphs that we're looking at here are going to be simple, unweighted, and connected graphs. And so when we have this graph, we can represent it in terms of a matrix as well. This is called the adjacency matrix. It is defined as being a n by n symmetric matrix, where the ij entry is either going to be a 0 if vertex I and vertex j do not have any edges connecting them, and a 1 if they have an edge connecting them. Technically, with the definition of adjacency matrix, you can have values other than 0 and 1, but since we are looking at unweighted graphs, we are limiting our adjacency matrices to just including zeros and ones. So now that we have our adjacency matrix, we can do several different things with it, all the traditional linear algebra processes like finding eigenvalues, eigenvectors. But what we are especially interested in looking at is the inverse of this adjacency matrix. So the inverse of a simple connected graph is also going to be a connected graph. And so we're trying to study the properties of the graphs with an inverse. So this was first looked at back in 1976. They found that a connected graph has a single graph as its inverse, if and only if it's just a set of trees. And so once we have our inverse defined, we can restrict our definition even further of an inverse to what is known as a sign inverse. And so this was first discussed in 1988 by Bucky, Doty, and Harary, who defined sign-invertibility as being if the inverse is a sign. So it's either going to be -1 or 1 on each edge. This translates into the adjacency matrix having entries of only 0, -1, or 1. So you're taking a simple connected graph and you're taking its inverse and you're getting out a simple signed graph. You don't have any value, you don't have any weights on any of these edges. So there's been some progress made in this field, but not a lot. In the original paper from Bucky and Harary, they found that a tree is sign-invertible, if only if it has a unique perfect matching. And then there really hasn't been a lot of work done in this area since then, until Kalita and Sarma came up with the result in 2022 that found for non-bipartite unicyclic graphs, there is a case where you can have, where it can be sign-invertible. And so lots of different, there's been work kind of around this, but ours is kind of a more general scope than a lot of these. So this was the original result. Unique perfect matching has a sign inverse when it has for a tree. That result will come to be important later. And then Akbar and Kirkland looked at it for bipartite graphs. And then most recently, Yang and Yi looked at all bipartite graphs, so not just the bipartite unicyclic graphs from before. So when looking at the inverses of these graphs, that is a huge area to cover, right? But we can simplify down the types of graphs that we have to look at by looking at the determinant of these graphs first. So we know that if the determinant of the adjacency matrix is not 1 or -1, then it can't be composed, then it can't sign invertible. It's the way that the linear algebra works out is if your determinant isn't 1 or -1, then you have some entry in your graph that is not 1 or -1. So if you have a graph with a determinant that isn't, we call it unimodular, if you have that condition, then it can't be sign invertible and you don't have to look at it anymore. So this was first looked at by Harary and Kirkland in 2007. They found that a unicyclic graph is unimodular if and only if it has a unique perfect matching. And that follows quite easily from this theorem from 1962, also by Harary. I'm sorry, which allows us to write our determinant in terms of a sum of the perfect matchings of this graph. So this theorem that allows us to look at to express the determinant in terms of the number of edge matchings of the graph, as well as in the terms of cycle matchings. And so an edge matching is when you are expressing the spanning subgraph of the spanning graph of the graph in terms of just edges, no cycles involved. A cycle matching has at least one cycle in there somewhere. And that comes into this part of the determinant here. So for unicyclic graphs, there's only, you will either have plus or minus 1 and then plus or minus 2. So if you have the unique perfect matching, like what Akbar and Kirkland were talking about, then you're going to be unimodular. Okay, and so this was another result from 2018, and this turned out to be extremely important for us with our investigations. So what this allows us to do is find for any two vertexes x and y, we can find the corresponding entry in that inverse, so like the xy entry in that matrix, in terms of the number of basically feasible paths connecting vertex x and vertex y. So what you do for this, and we'll get into more detail on this in a little bit, but you choose a vertex x and you choose a vertex y. You take every possible path between those two vertices. So you take a path, you eliminate that from the graph, and then find the determinant of what's left over. And so you take all of those possible feasible paths, add them up, and add their determinants up, rather. And that is your entry in your inverse. And so that's an extremely important result for us because it allows us to look at our graphs, our points on our graph. And if you ever have a path that when you add up all the determinants is not 1, -1, or 0, then you can just immediately stop. Your graph isn't going to be s-invertible because you found this entry in the inverse that is not 1 or -1. And so this is extremely important because it allows us to find our determinants without having to go through the full linear algebra style calculations on the adjacency matrix. Okay, and then this is one more thing that we have used a lot in our investigations. It's known as K2 reduction. So what this allows us to do is if you have a vertex and its unique neighbor, and they're just connected to each other with one edge and connected to one other vertex, you can eliminate those from the graph without affecting the absolute value of the determinant. So if it was unimodular before you took those vertices out, then it'll be unimodular afterwards. So that allows us to take these really complicated structures and kind of simplify them down even more. So just a little bit of terminology. We say that a graph is K2 irreducible if its if when you eliminate all of the possible vertices from the graph, all the possible K2 matchings from the graph, you are left with just one vertex. So that's K2 irreducible. In that case, it also has a determinant of 0. And then the graph is K2 reducible if, when you perform all of these K2 reduction operations, you get the empty graph. Okay, so with all of that in mind, we wanted to start looking at the see if we can find which unicyclic graphs were going to be s-invertible. So we were very quickly able to see from this result in 2007 that if you have a cycle without any pendant edges on it, it's immediately can't be s-invertible because none of your cycles are ever going to be unimodular. So we have to have at least one extra vertex attached to this graph in order for it to potentially be s-invertible. Let's see, K2 reduction. Okay, so we define peg vertex as just a vertex that would be that's on a cycle that would be eliminated with K2 reduction. And so these pegs are extremely important for our s-invertibility criteria, because what they run into is if you have a cycle with a peg, then going back to that determinant formula from earlier, if you have a cycle with a peg, then it is only going to have a edge matching, because if you right, so like for this graph right here, this is the simplest unicyclic graph with a peg that you can get. So we can match these two together, match these two together. If we're trying like the determinant formula from earlier, where it was 2 to the number of cycles, -1 to the number of edges, I believe. So this is one scenario. So it's 2 to the 0, -1 second power. So we've gotten that matching for it. If we try to go further and match this cycle, then we've isolated this one vertex out here. And so when you isolate a vertex, that makes the determinant of the whole graph 0. So this works out to be, this one turns out to be unimodular. And so what's important about this is if you have a cycle with a peg, then you aren't going to have that cycle matching. You're forced to have an edge matching instead. And edge matchings are much easier to deal with when you're looking at s-invertibility, because they're either -1 or 1. You don't have to worry about canceling out large numbers to try to get your inverse value back down to something smaller. Okay, so with that in mind, we got to our main result for the unicyclic graphs. And so we found what we call the peg condition for unicyclic graphs. So we say that a graph satisfies the peg condition if every cycle of the graph has at least 2 pegs. And then if that cycle does have exactly 2 pegs, then the two feasible paths between them, those 2 pegs, are not congruent modular 4. And I'll get into that with some examples in just a minute. But we were able to find that a unicyclic graph G is s-invertible if and only if it has a unique perfect matching, so it's unimodular, and also satisfies this peg condition. Okay, so, and this peg condition also extends quite nicely into the bicyclic graphs as well. That was a bit of a surprise, but I'm happy it worked out that way. Okay, so now with our graph, this is the graph that we were looking at earlier. In this case, it is not s-invertible. and we'll go through that and see why. So we are looking at for any two vertices, the number or the sum of the determinant when you take out the feasible paths. So like when you're going between, let's say, when you're going, if we set this vertex is equal to X, and this vertex is equal to Y, we can take this path, get from vertex X to vertex Y, and we're just left with this part of the graph up here. So that would be, the determinant of that is -1 plus, and then there's another possible path that we could take. We could go up through here, including the vertex, and then coming back down here. So coming back down here. And then this allows us to, hold on. Yeah. Okay, so if we come down here, we isolate just this one vertex by itself. So sorry, hold on. Okay. Sorry for that. When we take this path up here, it isolates this one vertex up here. So the determinant of what's left over is 0. So the entry in that part of the adjacency matrix is going to be -1. So that's okay. It actually works for any of the points on the cycle. And so it looks like this graph should be s-invertible, right? It's, it's got determinant of -1, it's got everything nicely. But there is one small problem. It's that when you're choosing your two vertices to look at the path between, you can also choose a single vertex as well. And so most of the time, this is okay. So if you take this vertex and eliminate it from the graph, then you leave just this. There's an odd number of vertices here, so it's just going to immediately go to 0 for its determinant. There's nothing to worry about there. And then the same holds for all of your vertices on this cycle. But then if you start by eliminating this peg vertex here, you start to have issues. So then you're left with just this cycle. And from the results earlier from Akbari and Kirkland, the determinant of odd cycle is either going to be, it's either -2 or 4. I don't remember which one. But either way, when you're looking at this formula, that entry in your inverse is going to be either -2 or 4. So because of that, we've got this entry in our inverse that isn't a 1 or a -1. This entire graph cannot be s-invertible. Okay, so let's go on to the next one. And this one is s-invertible. So this one meets the peg condition that we were discussing earlier. The last one did not, because it only had exactly one peg. So this is the second criteria of the peg condition with the 3 more pegs. We'll talk about the case for exactly 2 pegs in just a minute. So with this graph, this is a little more complicated, but most of the ideas from earlier still hold. Like if you have paths between any 2 ones of these on a cycle or any of these peg vertices, that's okay. Those entries are either going to be -1 or 1. You aren't worrying about isolating a cycle or anything like that. Anything that would make your value of your inverse not -1 or 1. So now let's look at eliminating the peg vertices, like what we did earlier that caused us trouble with the last graph. So if we take one of these, it doesn't really matter which one, and eliminate it. Then instead of being a cycle left by itself, it's this graph. And this graph is actually In this case, its determinant is equal to 0. And so that's fine. We can safely put this into our inverse, and the graph is still s-invertible. So for each of these, we can eliminate them, and we get the same result for every one of these. And so what you run into with the unicyclic graphs is you need those extra pegs on your graph to prevent it from having a cycle matching. That's ultimately, at the end of the day, the largest problem with the unicyclic graphs is when you get a cycle in your subgraph. Okay, so now on to the case with two pegs. There were some caveats there with the congruency of the paths, so I just wanted to go through those. So with this graph, we have two pegs. So with the paths inside the cycle, that's all fine. There's at most one feasible path between those, because if you're going from this cycle, this vertex to this vertex, and you come this way, then you isolate these two vertices, these two peg vertices, and you're left with a determinant of 0 for that path. So that's okay. We don't have to worry about that. If we eliminate one of the pegs, like what we were having trouble with earlier, we still have this one peg over here to prevent us from having a cycle matching. That's okay. So now there's one extra case that we have to consider. Because there's only two pegs, that means that there are two feasible paths between each set of pegs. Like for the last graph, if you wanted to have a path between this peg and this peg, you could come this way, right? And then you leave this by itself. If you try to come this other way, you would isolate this one vertex, and you'd have determinant of 0. So with three pegs or more, there's only one feasible path between each set of pegs. But with two pegs, then you have the potential for two feasible paths. And it turns out that gets tricky. So if we're going between this peg and this peg, we can take this path. And so the determinant of what's left over is -1 squared. So that's just 1. If we go this way, then we've used up all the vertices in the graph. And so by definition, the determinant of this part of when you use up all the vertices is also 1. So when you add these two up together, you get 2 for the XY entry. And so now, because of this entry, it's not going to be s-invertible. So this is where the congruency of the two paths between the pegs really starts to become important. Because you need, when you're doing these paths, you want them to have opposite signs so that they cancel each other out. Instead of that being 2, it's just 0. And so that's what that extra caveat was with the peg condition, that if there are two pegs, then the paths between them cannot be congruent modular 4. And go to the next one. Okay, and so for this one, it's also got two pegs, but in this case, it will work out. So if we look at vertex X and vertex Y, we can start again by taking this path here. And so we're left with this single vertex, or the single set of vertices down here. So that is -1 to the 1. So the value, this one's determinant is 1. If we come down this way, then we're taking all the vertices in the graph again. The value of that determinant is going to be 1. So when we add those together, we get this one is equal to 0 for our A negative. That's why. And so for this case, because these two aren't congruent, then everything works out. So the way that we define this is it's like the number of vertices here and the number of vertices here. So the first path was there's 0 for vertices there, and then there's 2 here. 0 and 2 are not going to be congruent when you do like 0 mod 4, that's 0, and 2 mod 4 is 2. In the last example, we had for our 2 paths here, we had 0 vertices and 4 vertices. So 0 mod 4 is equal to 0, and 4 mod 4 is equal to 0. So when these two are the same, we have issues with our sign invertibility. But if they are not, like in this case, then the 2 paths will, when we add them up, cancel each other out, and our graph can be s-invertible. Okay, and then this falls nicely into our results found by Kalita and Sarma in 2022, where they did the sign invertibility with at most with 3 or more pegs. We extended that to include the special case with 2 pegs. Okay, and so now with that, we will now move into the bicyclic graphs. So there are 2 main families of bicyclic graphs. There's either the barbell graph or the theta graph. So we define a bicyclic graph as a graph has either of these as its 2 core. So that's just that's just our terminology for if you performed all of your possible K2 reduction operations, and then you're left with a graph that looks similar to either one of these. And so like the unicyclic graphs, a bicyclic graph is going to be sign invertible if and only if its core graph is sign invertible as well. So with the bicyclic graphs, we looked at those, and we found that if you have a bicyclic graph with a barbell, we'll go through the barbell first, it's slightly simpler. Then it's going to be sign invertible if and only if it's K2 reducible, which means it has unique perfect matching and is therefore unimodular. And it also has to satisfy one of these following parts. So there's this one special case with the where it's a very small case of the bicyclic graphs, or there's the case where every cycle satisfies the peg condition. So going back to the unicyclic graphs, like each cycle in your bicyclic graph either has 3 or more pegs, or if it has 2 pegs, then it follows those special criteria from earlier. And then this is the special case for the bicyclic graphs. And so the reason that it works with just 1 peg, and whereas just having 1 peg didn't work with the unicyclic graphs, is if you eliminate this vertex here, then the determinant of what's left over inside here is 0. Previously, like when we did this case, and you eliminated 1 vertex, the determinant of what was left was not equal to 0, and it wasn't equal to 1 either. So in this case, it's just how the structure of this particular graph works. It's determined 0 as opposed to being -2 or 4. So that's why this one case works. And then, of course, the more general case is each of your cycles meets the peg condition from earlier. Okay. Okay. So moving on to the theta graphs. The theta graphs are a much more complicated part of the bicyclic graphs compared to the other families of bicyclic graphs, like the barbell and everything, because they have the ability to have 3 unique perfect matchings, or I'm sorry, not unique perfect matchings, 3 perfect matchings. And so when you get those 3 perfect matchings, then you have extra opportunities for canceling everything out with your determinant formulas and everything. So it just complicates matters a little bit, all those extra paths to consider. So there's like the bicyclic graphs, there is a special case where you have just 1 peg on the cycle. It's very similar to the example I showed you with the bicyclic graphs earlier. If you eliminate the peg, instead of having a determinant of that's not equal to 1 or -1, I believe it's equal to 0 again here as well. So it's just a special case of the structure. And then, or your other opportunity for it to be s-invertible is if every cycle of G satisfies the peg condition. There is, once again, one special case to that, and that is the crab graph. Oh, goodness. There should be an extra path here. It's the crab graph. So the reason that this one works is you have your 2. It's very similar to the unicyclic graph. It's basically just a unicyclic graph with an extra line drawn in it. So it gets into, you have for each vertex X and Y, you have now 3 feasible paths between them. So when you take this first path, you're left with these 2 vertexes down here. So let's label these path 1, path 2, and path 3. Path 1, you leave these 2 vertexes down here. So it is -1 to the 1. If we take path 2, then we eliminate this set and this set. So it's -1 squared is equal to 1. Path 3. 1, 2. Yeah, because we're coming down here. And we isolate this set up here. It's -1. So when you add them together, you get the -1 for this entry. And so it works in this particular case. Technically, not all the cycles in here meet the peg condition. And I'm sorry, I should have erased that one. That's actually part of the graph. I just didn't get it on my diagram in time. But it's a small case of the bicyclic graphs for the theta graphs. In general, for your theta graph, if your all of your possible cycles in here meet the peg conditions, then your entire graph is going to be s-invertible as well. Okay, and now the last case that we have looked at with sign-invertibility is what's known as the cactus graph. So the formal definition of the cactus graph is a connected graph where any 2 cycles share at least at most one vertex. We have limited that just a little bit with our thing. We say that they can't share one vertex. So like if you had 2 cycles, they could be joined at a vertex like this. What we're saying right now is that they are not similar to this one over here. I think that it should work. The should apply to this case where they do share one vertex, but we just haven't worked those cases out yet. Okay, so once again, there are no cactus graphs that are unimodular without a peg. So we can go ahead and immediately start looking at cactus graphs with pegs. Okay, so with cactus graphs, these actually work out to be much nicer than the other families. So it is going to be sign-invertible if and only if each unicyclic subgraph meets the peg condition. So I'm just going to go through the proof here kind of quickly. So for the first case, if you have a cycle that does not meet one of the conditions in the peg condition, like you have only one pendant edge and it's an odd cycle, or if you have two pendant edges but the paths are congruent to each other, then it's really easy to show that even if that's part of a cactus graph, it still can't be sign-invertible. So if you had the case where you had one and then it's off connected to something else, right? And this is all K2 reducible. We assume that because it has to be unimodular. So if we eliminate this part of this peg off of this cycle that does not meet the peg condition, then the rest of this graph will disappear during K2 reduction, and we'll just be left with this one cycle again. So that one can't be s-invertible. If we have a case where there's two pegs that are congruent to with paths that are congruent to each other, so not meeting the peg condition criteria, something like this, it's off connected to, and then there's more graph over here. You can really easily be shown that if you do this path and this path, everything else out here remains constant. So this will still be 2 or -2 like it was with the unicyclic graphs. So if you have a cycle that doesn't meet the peg condition, then you immediately cannot be s-invertible for your entire graph. Okay, so with the now that we have our cycles that all meet the peg condition, we now need to really start looking at the relationships in between each set of cycles. So if you have a cycle with 3 or more pegs, then you have at most one feasible path through that cycle that doesn't isolate a peg. So we don't have to worry about those as much. What you do have to think about with these cactus graphs is if you have a scenario where you have, draw this out real quick. So like this would be a cactus graph. These are two cycles that meet the peg condition with 2 pegs. And then this is the path between them. There can be anything that you want in here. You can have cycles with 3 more pegs. It could just be a tree. But you're wondering about like a path from like here to here, right? Like, is there a way that the parity of these paths can, cause us to get like a 2 or a 4 or some value that isn't -1 or 1, or will those cancel out? So what it gets into is you have for each of your set of vertices 2 n paths between them, where n is the number of odd cycles without outside pegs. So like when you can go, so like this is part of a cactus graph, right? This cycle has 2 pegs inside of it. you can either go this way or this way. So you have two choices when you're going through this part of the graph. What it gets into is, and then for each, you can have multiple cycles like this. So that will determine the number of feasible paths that you have between your vertices. What it gets into, though, is when you go here, you will have 2n-1 paths where you end up with it being congruent to 2 modular 4, and then you'll have 2n-1 paths where you end up congruent to 0 modular 4. And so when you end up adding those together with your determinant from earlier, is those will end up canceling each other out. And so that entry in your inverse is just going to end up being 0. So that case is fine. And then it can be shown that if you are going through so like we have a cycle with 3 or more pegs, if you go through and you isolate one of those pegs, then the graph left up there will also either be equal to 0 or 1. So you don't have to worry about the congruency of the paths inside of your cactus graph. You only have to be concerned about the paths inside of the individual cycles themselves. And so that really simplifies it, and that's what allows us to get at our results where your cactus graph is only s-invertible if and only if each of those unicyclic subgraphs meets the peg condition. And so I think that this should extend to the full definition of the cactus graphs, where you can have the cycles sharing one vertex. I think that instead of saying every unicyclic subgraph meets the peg condition, you would say either every unicyclic subgraph meets the peg condition, or any bicyclic subgraph is s-invertible. So just to cover that special case where you have 2 cycles joined at a vertex. All right, and so just as like an example of some of the ongoing research into this, Zafar and Kalita recently talked about which graphs have weighted trees as inverses. And so that's a really interesting kind of that's a really interesting part of this. So with the weighted trees, that is going to be a s-invertible graph, but it also has extra requirements on like the structure of the graph. So like when you get your inverse, it's not necessarily guaranteed to be connected. And so they're looking at, is it a tree or something like that? And then another thing that I would like to look at this area in the future is, can we say that all graphs composed of cycles that meet the peg condition are s-invertible? So we know that the inverse of this is not true. Not all s-invertible graphs have to meet the peg condition. There's the crab graph. There's other examples of the bicyclic graphs that disprove that. But looking the other way, that could still allow us to categorize a fair number of s-invertible graphs by themselves. And yeah, that's all that I have. Are there any questions?
I stop the recording and feel free to unmute yourself and ask the speaker.